Okay, for this fourth test, I'm going to try something new, and I'm going to make a video of me tutoring, and that can actually go along with the study guide. So if you bought the study guide, this will go perfect with it because it's just me answering every single question. If you didn't buy a study guide, then this is the same thing as a study guide, but me actually talking, so it'll work either way. So I'm just going to go question through question. No. Okay, so I just go question to question. Okay, so the first question is know and understand the principle of Archimedes and how it applies to the procedure of human body values and what the Archimedes principle is and underwater weighing and all that good stuff. So basically Archimedes just found out if you place an object in a solution or a fluid, it'll displace a certain amount of water, of course, and the volume of that water displaces is equal to the volume of the individual or the object in the water. So this is useful in order to find out the volume of a person, which in volume of a person you can find out the density of the person. So it's using underwater weighing, which is a gold standard in body composition to find the percent fat of someone. So pretty much you place a person in the water and they'll displace the volume of water, and then you can measure the volume of water using a scale and whatnot. And then this volume of water is equivalent to the volume of the person. And then when you know the volume of the person, you can find the density of the person based on the formula of density equals mass divided by volume, and the mass of the person is literally just you weigh the person. And then based on the mass divided by the volume, you find the density, and then there's other formulas that you don't need to know, you won't have to calculate or anything, but then you can plug in the density into certain formulas, and from that formula you can find the percent fat that someone is. And that's underwater weighing, and that's considered the gold standard. That's underwater weighing, and that's considered the gold standard in body composition. Okay, the second question. Understand the differences and usefulness of different body compositions and anthropometric assessment procedures discussed in text and class. What are the general assumptions used by the indirect measures? Okay, so to measure body composition, you have the basic one, skin fold. Everyone knows what skin fold is. You have another shitty one called bioelectrical impedance. Underwater weighing, which we just talked about, which is the best one. X-ray, and the bod pod, which you probably didn't talk about. So skin fold is the most common one. You can give this to leech. All this involves is taking calipers and pinching 7 areas of your body or 3 areas depending on who's doing it and how accurate you want. And this is based on the theory that, because since you're just pinching the skin, it's based that a majority of your fat is close to the surface of your body, so most of the fat is subcutaneous compared to visceral. And if most of it is compared to the surface of your body, when you measure like a certain centimeter of the skin or something, you can plug all this stuff into a formula, and this formula will tell you the percent body fat. Blah blah blah. 7 skinfold sites of calipers, they'll plug into a formula. Okay, you won't have to know. I don't know if you have to know, but when you do skinfold and when exercise testing, when you get to, you're gonna have to demonstrate skinfold testing. You'll get graded for it, but all pinches have to be made on the right side of the body. I'm not sure why it's the right side of the body. There's really no difference, but that's the way that it was first invented when they first started doing it, so you always have to do it on the right side of the body. It's kind of accurate, fairly accurate. It can be up to 4% off depending on how much the person sucks and taking the skin pinches, they take in the right spot, etc., etc. And since it's measuring just the thickness of your skin, pretty much it can be affected by many things, like if you're dehydrated, if you're hyperhydrated, whatever. So it's not really the best. If you just exercise, your skin gets thicker, so that's going to skew the results, so you can't do it after you exercise. And it changes with age, which might be a question, because the older you get, your body stores more fat viscerally, which is closer to your organs, so it's protecting your organs. And since it stores more fat closer to your organs, the older person will have less fat subcutaneous, and their results will be skewed. And the underwater weighing, which one we talked about, that's considered gold standard. That would definitely be a question. What's the gold standard of body composition? It's underwater weighing. But it's not that. The downside is it isn't really that practical. Not everyone has a pool they can sit in or is willing to be loaded into a pool to measure the volume. But skin fold you can do anywhere, but it's not that accurate. So pros and cons of each one. And the NOI weighing is based on the fact that fat is less dense than water, so the more fat someone has, the less they'll sink. The more muscle they have, the faster they'll sink, because muscle is heavier. Okay, the next one, bioelectrical impedance, is abbreviated BIA. So you might write BIA or say bioelectrical impedance. And this is a stupid handheld thing where you just, it's like a machine, you just grab it, hold it with your hands for like 2 seconds or so, and it tells you your percent body fat. It's extremely stupid, not that accurate. If you ever use a bioelectrical impedance, don't listen to it, it's bullshit. Because it's based on the fact it sends electrical signal through one side of your body, the right side of your body, I believe, through the machine, and goes to the left side of your body. And then it measures your percent body fat based on how fast the electrical signal moves, with the theory that since fat conducts electricity and muscle does not conduct electricity, because if you have fat, more adipose tissue, etc., conducts electricity faster, just conducts electricity. So the more fat you have, the faster the signal will travel, and it predicts it from that. And the less fat you have, you don't have any less fat you have, the more lean mass that does not conduct electricity, as well as fat, so the signal will be slower. And based on how fast the signal moves, it estimates the percent body fat. Now, there's a lot of things that can be wrong with this, just based on depends on how fast the signal moves. So, say you have too many electrolytes in your system, or you just ate a banana or a lot of bananas, or you just ate or something. So you have a lot of electrolytes in your system. Electrolytes conduct electricity, obviously, so that will skew the results, and it'll make the signal move much faster than before. So that will say you have much higher percent body fat than you would have if you did not just eat. Well, if you just exercised, you just sweated a lot, so you lost a lot of electrolytes. And then you'll conduct the signal even slower, so it'll say you have more muscle than you do. Say you're leaner than you really are. If you're dehydrated, blah, blah, blah. Can be conducted if your skin is warm. If your skin is cold, that can affect it. You have to know that if your skin is warm, then it will travel faster. The current will travel faster. If your skin is cold, then the current will travel slower. If it travels faster, it says you have more percent body fat. If it travels low, then it says you have less percent body fat. So pretty much, this is a horrible thing. A lot of things can affect it. It's not that accurate at all. Once when I did it, it had me at 2% body fat, and then 10 minutes later I did it and it had me at 6% body fat. And within that time I drank a lot of water. So a lot of things can affect it. So BIA, bioelectrical impedance, isn't that good. And then you have X-ray. X-ray is mostly for bone, to see fractured bones, everyone knows that, but can also calculate fat mass from this. Blah, blah, blah. In BMI, you have to know how to calculate BMI for sure. By the time you graduate this major, you'll be a pro on BMI. BMI is just a number that estimates how much lean mass someone has. And it's just kilograms divided by meters per squared. So it's individual it's not really individual. It's individual for the person, but the range is like obese, underweight, normal, obese, and extremely obese, and are based on populations. So it's not really, BMI is good to go by, but it's not the best thing to go by, because someone, like say 2 people that are 70 inches or 5'10", and one person's extremely has a lot of muscle, they're like 190 pounds. One person's very skinny, they're 130, but they're both healthy. The 185 person, based on the BMI formula, if you solve out kilograms divided by meters squared, you have to convert their weight, 185, to kilograms, which is just divided by 2.2. You convert their height in inches to meters squared, which means you have to do inches times 2.54 to get to centimeters, divided by 100 to get to meters, and then just square. Have the 185 person, I believe, it'll say they're very overweight, or they're overweight, almost obese, and clearly they're not obese, they might be overweight, but they just have a lot of muscle. So it doesn't take into effect the body composition. So BMI is good for the general population, but for one individual, depending on how much muscle they have and everything, it's not too great. So BMI is anthropometric measurement. Anthropometric meaning you can easily take it as height, weight, BMI. It's kilograms divided by meters squared, so you just take their height, their weight in pounds, divide by 2.2 to get to kilograms. You have to know that conversion for sure. And their height will be in inches. Just do 12 times how many feet plus inches. So 5'10" will be 12 times 5, 60 inches, plus 10 more inches, 5'10", that'll be 70 inches. You take 70 inches in this times 2.5 centimeters, because each inch is 2.5 centimeters. To convert to centimeters, divide by 100 to convert to meters, and you square that. And you just take those two numbers and divide it. And you have to know the ranges for all the BMIs. They can either be considered underweight, normal, overweight, or obese. Or there's also obese 2, obese 3 once it gets to extremely high numbers. And you have to know these ranges. Underweight is below 18.5. So if someone's below 18.5 BMI, they're underweight. Normal is between 18.5 BMI or 18.6, 18.5 BMI, sorry, to 24.9. So you have to know 24.9 is the cutoff, not 25. And then once you get over 25 to 29.9, you consider overweight. And then 30 to 34.9 is obese. Higher than 35 is considered very obese. You won't have to know the different categories of obese, just if you're higher than 30, it's considered obese. You just have to know those ranges. And again, it's not the best measurement for fit people. It's good for the general population, but if you take a very fit person, like a runner or something, they're naturally going to be very light, but clearly they're in shape and their heart is very strong and they're healthy. So it's not that good for fit people. And then another one that's much better than BMI is waist circumference. And this is just taking a tape measure or a measure and just putting around the waist. And then that will give you the measures the abdominal region in inches. And then this is more predictive for heart disease, because when fat is more abdominal, it's more predictive for heart disease. So that's what we care about. We want to control our abdominal girth and weight. So fat in your abdominal, you don't want fat in your abdominal region. But the best one is underwater weighing. That's the one that he's going to want you to know. Underwater weighing. Who asks what is the gold standard? Underwater weighing. Okay. 3. What are the body composition differences between male and female? So everyone knows males have less body fat. It's just part of their physiology. They have less body fat because women have more body fat because they have to have children. So thus they need more fats for childbirth, and men don't have childbirth, so they have less body fat. For men, you need 3% body fat. That's considered essential, since fat does a lot of things besides just making someone fat. It's for insulation, protection, fluid transport, all this stuff. So and it protects your organs, protects against shock, all that stuff. So you need some fat. So 3% is considered essential for men, and for women, 12% is considered essential, because this is the required fat, adipose, or fat that they need to run their menstrual cycle, their hormones, and be prepared for childbirth. So they need a lot more fat than men. So 12% is essential in female, 3% is essential for males. The main thing being the menstrual cycle and hormones for females. Okay, number 4. Understand the difference between the essential fat and the storage fat. Essential fat is the ones you need. Obviously, it's essential. Storage fat is just extra fat that you don't really need. It's just there. And differentiate between FFM, or fat-free mass, and LBM, or lean body mass. Okay, so essential fat, again, is what all the organs need to function. If they don't have these fat, then they can't function. Because if you remember, phospholipids, which is found every bilayer of every single cell, are made of fats, not triglycerides. Cholesterol is made, from fat diets. You need cholesterol. It cushions organs. You just need this essential fat. So remember, it's 3% for men, 12% for women. So storage fat is just what you're just storing. It's just extra fat. It's stored in adipose. It just stays in your body. And the easy difference between fat-free mass is just like what it says, fat-free mass. It's mass that's not fat. Lean body mass being muscle. Very simple definitions. Okay, so 5. How does energy balance and weight loss affect body composition? Everyone knows the basic formula. If you consume more calories than you burn, you'll gain weight. So if you burn more calories than you consume, you lose weight. And that's basically what it is. If you consume more calories than you burn off, or blah blah blah. If you consume more calories, they'll be stored as adipose tissue. They just stay there. They're not wasting the body. Your body doesn't need to use them, so it'll just store it and keep it in adipose. Now, the things that affect your metabolism that you'll need to know. There's 3 things for your metabolism. It's a combination of 3 factors. You have the thermic effect of food, which is just how much energy it takes to digest and absorb each macronutrient. So proteins, fats, and carbohydrates. They all take energy to actually break them down. And proteins, you need to know, take the most energy to break down. So thus, it's better to have a diet high in proteins than anything else. Because proteins are also the thing that fills you up because it takes the most energy to break down. So protein is good. Thermic effect of food. Activity level, of course, how much activity, how active you are, how many calories you burn, that's going to affect your metabolism. And your resting metabolism. Your resting metabolism is how much calories your body burns to actually just to stay alive. So it's considered, just think of it as your resting metabolism as the calorie requirements to live. So you need a certain amount of calories. It's usually 1,500 to 2,000 calories a day your body takes just to live, just to breathe, to run its organs, to run your kidneys, your liver, just to do all its metabolism. So everyone is burning a certain amount of calories every single day just to live. And also, the more muscle someone has, the higher their resting metabolism will be, because more muscle means it takes more energy to run, more fuel. Which is why when people work out, the more muscle they have, the higher the metabolism is. Okay, so 6, understand the potential impact on diet and exercise on obesity. You have to know what is the differences if you just diet alone, if it's as effective as diet plus exercise. Which one's more effective in obesity, which one affects like losing weight, lean body mass, just which one you want to do. Okay, so basically, as everyone's probably guessed, it's better to do both exercise and dieting, but you'll have to know which ones affect what. So if you just exercise alone and not do anything with your diet, you're exercising your ass off, but you're eating like shit, clearly you're not going to get any results. You'll still get results because you're exercising, but you're not going to lose any weight or anything, and you won't see results really. So exercise is not as effective as cleaning one diet, so you want both of them. You don't want just exercise. Because no matter how much you exercise, if your diet sucks ass, you're not going to lose weight. And then if you just diet, you control your diet, clean up your diet, but you don't do any exercise, you'll probably lose weight, or you will lose weight, you'll lose fat, but you're not going to gain any muscle. You're not going to gain any lean muscle, so you're not going to gain any lean muscle, you're not going to look better, you're not going to be toned. So clearly you have to do both exercise and diet. That's the best combination. And then he gave, in my class, when he gave, I don't know if he gave in your class, he gave a little study that he shows that if you just diet, there's a group where they diet alone, there's a group where they do exercise, and then there's a group that diets and exercises. Then he looks at them and sees and compares on sees which one's better. The diet only group lost weight because they were dieting, so they lose fat, but they did not gain, but they could enhance the weight loss if they exercise. That's common sense. Now the exercise alone group also lost weight because they lost fat weight, and they gained lean body mass. But if you combine exercise and dieting, you will lose much more weight, and you'll also gain lean body mass. So you want to lose weight and gain lean body mass. So exercise and control your diet is the best combination. I don't know how much detail you went into that. Okay, number 7 is understand the concepts of the energy balance equations. These are the equations that we kind of went over or hit briefly in number 5 with the 3 things with the thermic effect of food, the activity level, and the metabolism to give a total your basic metabolic rate. That's what it's called. So the basic metabolic rate is how many calories it takes to do everything in your body, all the normal functions, all the metabolic reactions in your body, to run your organs, supply muscles with energy, to excrete waste products, etc. Now the basic metabolic rate is usually, like I said, around 1,500 to 2,500 calories. There's a formula, which I don't think you have to know. It's based on age is one factor, weight is another factor, and height is another factor. The older you get, the lower your metabolism gets. Your weight is a factor because the more muscle you have, or the more fat, the heavier you are, based pretty much the higher your metabolism is. The more muscle you have, the higher your metabolism is, your basic metabolic rate is, because more muscle takes energy to run. So the more muscle you have, the more beneficial it is, and the more calories you'll burn in the long run in the basal metabolic rate. But also the same thing is true if you're fat or if you have a lot of excess weight. The more weight you have, the more stress that is on your bones and adipose tissue, that also takes more energy. So really, the heavier you are, the higher your metabolism is, but you're also heavier, so it's not really worth it. And now the formula is called the Harris-Benedict formula. I don't know if he wants you to know that, but if you want to know it, you can just Google it, which I'm sure you have it. This is just a long formula with numbers that you plug in the age, weight, and height, and it actually calculates the metabolic rate. Okay, so now 8 is what changes in fat cells when you lose weight and when you gain weight. So fat cells or adipose tissue, adipocytes, fat cells. Now if you lose weight, they just get smaller. If you gain weight, they get bigger. But what happens when you first, like you have a certain amount of adipose tissue, say you have 2 adipose tissues or 2 adipose cells. They can all hold a certain amount of fat. So when you first gain weight, first they're going to hypertrophy or they're going to get bigger. So the more fat's coming into the cells, and the cells keep getting bigger and bigger. But eventually, once they have a certain capacity, and once they reach this size, they will multiply. And when they multiply, that's called hyperplasia, if you remember from the third test. And fat cells are the only cells, adipose tissue are the only cells in the human body that go through hyperplasia or just they multiply. Remember muscle cells, when you work out and everything, muscle cells hypertrophy or they get bigger. They don't actually multiply, you don't get more muscle fibers, so you don't have hyperplasia. But adipose tissues are the only cell in the body that multiply and get bigger. So they get bigger and they multiply. So first they hypertrophy, they get bigger, they reach the limit, and then they actually multiply in hyperplasia. And they'll just keep multiplying as you get more fat, and they'll store the fat. Now the thing is, once adipose tissues multiply, say you had 2 adipose tissues before, they multiply and now you have 6 or 600. So you have 600 adipose tissues. Now the thing is, even when you lose weight, the adipose tissues will shrink because they have less fat in them, because you don't have as much fat in your body, but they shrink. But once you have 600, even if you lose 200 pounds or whatever, you're still going to have 600 adipose tissues. So once they multiply, you're stuck with that number. You're never going to decrease in adipose tissues naturally, unless you have like surgery or something, or liposuction, whatever. But once you have a certain number of adipose tissues, once you multiply already, once you've already gained weight and the adipose tissue multiply, you're stuck with those adipose tissues even if you lose weight. And this explains why once someone loses, like say someone's 300 pounds, they lose 100 pounds, and then it's extremely easy for them to gain weight again because they already have this abundance of adipose tissues to hold extra fat, so it's much easier for them to gain weight. So you gain weight, you get more fat cells, you lose weight, and you always have the same amount of fat cells, which is why it's very hard once someone's obese, it's very hard for them to keep the weight off. Okay, number 9 is what is BMI, which we kind of explained, but we'll talk more about what BMI is and the relationship of BMI to disease. Okay, BMI stands for body mass index. And the units for BMI are kilograms over meters squared. So you just take the kilogram of someone divided by meter squared. So let's take, for example, let's do my BMI. I am 155 pounds, so you take 155 divided by 2.2, since they're divided by 2.2 to get to kilograms, and this will be around 70 kilograms. So now you have your kilograms. Now I'm 5 feet 10 inches, so you got to convert 5 feet 10 inches first to inches. So you just take, that's 70 inches, and then you times that by 2.54 to get to centimeters first. So you times it by 2.54, which is like 200 and something centimeters, or it's 300 and something centimeters. And then you divide that by 100 to get that to meters, and then you square it. And that's like 3.14. And then you just take 70 divided by 3.14, and then you get my BMI, or 22 something. So my BMI is 22 something, and then you look at the category that 22 fits into, and that's considered normal. Again, BMI is not the best number to go by because you take me, 5 10 inches, 160, 155, whatever, and then you take a bodybuilder who's also 5'10", say they're 190 or something. Now, clearly, the 190 person would be considered, based on the BMI standards, they'll be considered overweight, but they're not overweight because they just have more muscle, and they're still healthy, just as healthy as me, but they have more muscle, so the BMI places them in a risk zone. So you have to look at the person. You want to use common sense. You don't want to just look at the number. But it's good for population. So, okay. Okay, so now how does it relate to disease? Now, really, how it relates to disease is based on, like, you really don't care about this number unless it's above 30. Once it's above 30, then they're considered obese. And usually, like, no amount of muscle, well, normally, you can't, like, work out and build muscle to get above 30. It's not going to put you above 30. It might put you overweight, but you can't get above 30 by just muscle. If you're above 30, you're usually obese. And if you're obese, obviously you're going to change your lifestyle. The reason for this is, as we all know, fat is stored mostly in your abdominal region, so around your waistline. And when fat is stored around your waistline, this is worse than when fat is stored in your hips. Because the more fat is stored around your waist, your pancreas is also close to your kidneys, down here, where the fat will be stored. So the more fat you have in your abdominal region, the harder your pancreas has to work, and this will affect insulin resistance, or your insulin. And insulin resistance means that you release insulin as normal when you have high blood sugar, and normally the insulin will cause the blood sugar to enter your cells, but insulin resistance will mean your cells are more resistant to the insulin, so the insulin doesn't work as well, so the blood sugar can't get into your cells, and this is what the pathophysiology behind diabetes. It's mostly caused by weight gain. That's for type 2 diabetes. So insulin resistance. So obesity usually leads to insulin resistance, and then that's when a bunch of cardiovascular problems will start. Okay, so number 10, we kind of went over what are the common techniques used to assess body composition. That's all the ones with the skin fold measurements, the BIA, the underwater weighing, the X-ray, and everything. And again, the underwater weighing is considered the gold standard, and that's the best one you want to do. Underwater weighing is the best one, but skin fold is the easiest one to do, but it's not the best one. But he's going to ask which one's considered the gold standard, and that's underwater weighing. Okay, so now 11. How do the skin folds and girth measurements provide meaningful information about body fat and its distribution, or where the body fat is in the body? Again, the skin fold measure is based on the theory, since you only pinch the surface of the skin in 7 different parts of the body, and you use the thickness in millimeters to plug into a formula, and you can get the body fat percentage. And this is based on a theory that majority of your fat is subcutaneous, or close to the surface of your body, because if majority of your fat was visceral, then this technique wouldn't work at all, because you're just measuring the surface of your body. So you measure the subcutaneous fat, and that's what skin fold is based on. Now girth is the waist measurement, or waist circumference, which is measuring the abdominal fat, which is a lot better than BMI. And again, because abdominal fat is more predictive of cardiovascular problems, and because you don't want fat stored in your abdominal region. Again, so waist circumference is more important than BMI, blah, blah, blah. And I don't know if you know the ranges of waist circumference, what's considered good, at risk, etc. Okay, so 12, I guess he wants you to know the 7 regions that you take for skin fold measurement. Know the anatomical locations for frequently measured skin folds. So 7 skin fold measures, you always take these 7 measures. You can also do a 3-site test if you're short on time, or you're doing a lot of people, but it's not as accurate as taking 7 measures across the body. Okay, so all skin folds again on the right side of the body. That can be a question. And it's basically just taking calipers and pinching the skin in 7 different parts of the body. And based on how good the person is who's measuring, how good the calipers are, a lot of things can affect it. So first, the 7 measures, you'd ask someone to take off their shirt, so you don't get the shirt fabric, and that can affect the measurements. So first, you take one diagonally at the chest, on the right side of the body. So you would take it right here. Don't have to show how to do it, but one diagonally on the right side of the chest, right here. And you take one vertically and subaxillary, or right above your, pretty much right next to your belly button. That's what subaxillary means. That's the next one for the abdominal, right above your belly button. So that's two. So one in your chest diagonally, one right above your belly button on the abdominal region, it's vertically. Then one subaxillary, which means in between your armpit and your, so right here, between your armpit, just right here. One suprailiac, and suprailiac, supra right above iliac, your hip bone, so just right above your hip bone vertically, diagonally. And you take one in the tricep, so you just take it right here on the tricep. And you take one in the thigh, and then you take one in your very back. So there's 7 measures. So there's 7 different places you can take. You take different skin folds, and then based on the 7 spots, you plug them into a formula. Well, the formula requires you to add up all those numbers from the 7 spots you just took, and then you plug into a formula. And there's also other tests to do a 3-test zone, 3-test zone. Okay, so that's all about body composition. So we'll just review very fast about body composition. Number 1, understand Archimedes, understand how underwater weighing works. Based on you submerge someone, you get the volume, because the volume, you get the volume of water displaced. The volume of water displaced is equal to the volume of the person. If you know when you know the volume of the person, you can get the density of the person by taking mass divided by volume to get the density. And then when you get the density of this person, you can plug into a formula, and then the formula will give you their percent body fat. You won't have to do a formula on test because you can't calculate on test. And that's underwater weighing. 2, know the ways to measure body fat. Underwater weighing being the best one. Skin folds that we talked about, just easily take the skin fold test, plug into a formula. Always take on the right side of the body, and it gets percent body fat. Many things can affect it, whether you're dehydrated, hydrated, if you just exercise, or how old you are. The older you get, the more fat moves visceral, so this test will be kind of useless. Underwater weighing, gold standard, know it. BIA sucks. Based on electrical current, you just have to know that's going to be based on electrical current, because you probably ask what it's based on. He's probably going to ask, like, if current's moving extremely fast, what does that mean? If current's moving extremely slow, what does that mean? The faster it moves, fat conducts electricity, so the faster it moves, theoretically, the more fat you have in the body, but many things can affect it based on electrolytes, etc. The slower it moves, the less fat you have, because muscle will impede the electrical signal, but many things can affect it. And then you have X-ray, which it's mostly for bone mass, but you can calculate fat mass from that also. And then you have BMI, which is just weights in kilograms divided by meters per square, or height in meters per square. And this gives you a certain number. And based on this number, you can classify someone as underweight, normal, overweight, or obese. Underweight being below 18.5. Normally people don't have a problem with the ranges. They have a problem with what is 18.5 considered? 18.5 is actually considered normal, or normal. So I call it normal, because below 18.5 is considered underweight. From 18.5 to 24.9, not 25, is considered normal. But once you pass 24.9, you get to 25, then you're considered overweight. So 25 to 29.9 is considered overweight. Above 29.9 or 30 and above is considered obese. And again, this isn't the best way to go by, because it doesn't take into account the body composition. It's based on the population, so overall in the whole population, since the whole population isn't bodybuilders, this is a good value. But if you're looking at just one individual, it's not really the best number to go by, because you have to let you look at the person and see if the body composition. And then the other one, waist circumference, that just measures the abdominal girth, takes centimeters, measures how big the waist is. And that's usually measuring the biggest part of the waist, so it's usually like right above the belly button, but it can be different on every individual. And that's better than BMI, because the more fat that's stored in your abdominal region, it's worse. Because fat in your abdominal region is more linked to cardiovascular disease. Again, underwater weighing, best one. What is the body composition differences between male and females? Males have less body fat than women, because they don't go through a menstrual cycle, they don't need all the hormones for childbirth and all that good stuff. So men only need 3% fat to be considered essential, women need 12% fat. You have to know those numbers. And again, that's because of the menstrual cycle. Know the difference between essential and storage. Essential is essential. It covers your bones, etc. Storage fat is storage. So what it says, fat-free mass is mass that's not fat. Lean body mass is muscle. Okay, how does energy balance and weight loss affect body composition? Basic formula: you burn more calories than you eat more calories than you burn, you're going to gain weight. It's going to be stored as fat. You burn more calories than you eat, you're going to lose weight. Again, the things that affect your metabolism, you need to know what the thermic effect of food is. That'll be one question probably. And which one has the highest thermic effect of food, and that's proteins. They take the most energy to actually digest. Because you have to break down, if you remember from metabolism, you have to break down every macronutrient to its simplest units. And that takes energy. Protein has the activity level in your resting metabolism, with how much calories it takes to actually live and supply your muscles and energy and constantly supply energy to them. Understand the potential impact of diet and exercise on obesity. As obvious, it's best to have diet and exercise. You want to have both of them. They have more positive effect than exercise and obesity by itself. And the reason being because when you just diet, if you just diet and don't exercise, yeah, you'll lose weight, but you won't gain any lean body mass. And ultimately, you want to gain lean body mass because that's more important. Well, it's not. It's probably as important as losing weight. So you want to gain lean body mass to make your bones strong and all that good stuff. So you want to exercise and diet. And then vice versa, if you exercise but your diet sucks ass, you're not going to lose any weight. You're gaining lean body mass because you're exercising, but you're not going to lose any weight. So you just combine both of them is better. Number 7 is understand the concept of energy balance, raise the metabolic rate, things that affect it, how much energy you burn every single day. Based on your age, the older you get, the lower this number gets. If you look at the formula, based on your height, your weights, the heavier you are, the more muscle you have, the higher your metabolism is. And also based on your height. The taller you are, the higher your metabolism is. You can just look at the formula. And the formula is called the Harris-Benedict formula. I don't know if you have to actually know how to do it, have to actually calculate it, but you need to calculate if he does ask you to calculate it. But if you look at the formula, the 3 factors you just plug in, it gives you certain numbers that are just set in the formula. They're constants, and then you plug in the age, you plug in the height and the weight, always in kilograms and centimeters. Well, in this case, height will be in centimeters, I believe. 8 is the changes in fat cells. Again, when you gain weight, fat cells first increase in size, and then they'll multiply once they reach a certain size. So they first hypertrophy or increase in size, and then they hyperplasia or increase in number. And know that adipose tissue are the only cells in the human body that go through hyperplasia. But once they hyperplasia and they multiply, no matter how much weight you lose, you're stuck with those fat cells for life. So if an obese person loses weight, their adipose cells get smaller, which is good because they lose less fat, but they don't decrease in number. So they always have the same number of adipose cells once they gain the weight, which is why it's so easy for them to regain weight because they have so many adipose cells. What is BMI? How is it related to disease? Again, we went over this multiple times. What BMI is, kilograms divided by meters per second. It gives you a number you can plug into different categories, whether someone's underweight, overweight, or obese. Why is this important for disease? Because normally when someone is obese, they most likely, majority of the fat will be stored in the abdominal region. And when we get to cardiovascular disease, abdominal fat is more predictive of heart disease because of insulin resistance, mostly because of insulin resistance. Put stress on the pancreas, and you mostly become diabetic. And once you become diabetic, you have a whole host of other problems. 10 is just repeating the body composition things. 11 is what is the skin fold again, the waist circumference. 12 is asking for the skin fold sites, the anatomical locations. Remember that skin fold is always done on the right side of the body, not the left side of the body. And that skin fold, you pinch the skin, and then you take all these numbers in millimeters, and then they plug into a formula. 7 areas, skin fold measurements. I don't know if you need all. I'm guessing you do know all 7 of them since you asked. So you take one at the chest diagonally. You take one in the armpit, subaxillary, right here. And you take one super iliac, so right above the hip bone diagonally. You take one in the abdominal region vertically, and then you take one in the back subscapular, right on your scapula, and then you take one on your thigh. Always on the right side of the body, and then you put these in a formula, and then you get body fat. Or there's also a 3-site method. if you want to save time, but it's not as accurate as a step-by-step method. Okay, so now moving on to the next section on heart disease risk. So 13 is, again, just a repetition question, pretty much. How is obesity related to cardiovascular disease? And he says, like, he sometimes refers as CHD, or coronary heart disease, or CVD, or cardiovascular disease. In this instance, they're interchangeable. They both mean the same thing. But cardiovascular disease is like a broad category for any disease that affects the cardiovascular system. So it might not just be coronary heart disease, what affects the heart. It could be a disease that affects the blood vessels or something. But it's any disease that affects the cardiovascular system. Whereas CHD, or coronary heart disease, is disease that affects the coronary arteries of the heart. Most likely it's atherosclerosis or hardening of the arteries. But in this case, we use it interchangeably. So first thing, obesity is bad for the heart. Blah, 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 explaining why. The simplest reason being because of abdominal fat. Bad for, it leads to diabetes, and that's a whole nother problem. And obesity is, like, once someone's obese, they usually have dyslipidemia. And dyslipidemia, just like anything with the word dys, the prefix for dys means abnormal, bad, lipidemia, lipid levels, so HDL, LDL, or in cholesterol. So they have really bad HDL level, LDL levels, or cholesterol. So high cholesterol, high LDL, low HDL. And we'll talk more about the lipoproteins or dyslipidemias with HDL and LDL later, but the more obese someone is, the more the heart has to work, because it has to pump blood fast to get to the organs, because the organs are actually farther from the hearts because they're so big, but not substantially farther, obviously, but the heart has to work harder. That's the main thing. The heart has to work harder, has to pump harder. And then when we go over LDL and HDL, that can lead to atherosclerosis, which is just hardening of the coronary arteries. And remember, the coronary arteries are the arteries that supply blood to the heart. So if these harden, or plaque gets in the way, or they occlude the blood flow, the heart can't get blood. And the heart can't get blood, heart's on the left side, if the heart can't get blood, then the hearts will die. And that's literally what a myocardial infarction is, or a heart attack. The heart's not getting enough blood, so a section of the heart, hopefully a section of the heart, not the whole heart, but a section of the heart dies, and once part of the heart dies, it's dead for good. Okay. Now 14 asks us for the CHD, or coronary heart disease risk factors, what are the major risk factors and why. Now coronary heart disease is a multiple factorial disease, so there's many factors that affect this disease and lead to this disease, not just one factor, like if you're just smoking, will affect this disease. But usually, since it's multifactorial, many things affect it, but all these factors depend on another factor. So usually if you have one factor, like if you're obese, you're usually inactive, obviously. You usually have dyslipidemia. You usually have high blood pressure if you're obese. So one factor builds on another factor. Now there's 8 risk factors, and when you get to exercise testing, you'll go into much more detail about the risk factors, and you have to classify someone as high risk, medium risk, or low risk. But the 8 risk factors, there's 2 non-modifiable risk factors, so you can't do anything about those risk factors. But 6 of the risk factors you can affect. You can change for the better. And the non-modifiable ones you don't care about, because that's age and family history. You can't really do anything about those. But the 6 modifiable ones are like smoking, obesity, high blood pressure, dyslipidemia, physical inactivity, and the last one, glucose intolerance, or whether you're diabetic or you're fasting glucose levels. You can do something about all of those. And again, all of those usually affect one another. So if you have one of them, if you're diabetic, say you have high fasting, you have high blood sugar, then most likely you're obese. Most likely you're, well, actually you probably haven't been smoking, but most likely you have dyslipidemia. They all build on each other. So for age, the numbers for the risk factors are, if a man's older than 45, that's just considered risk factor. That's an automatic risk already. If a woman's older than 55, it's considered an automatic risk. And the reason it's higher for women compared to men is because women have estrogen and they have a menstrual cycle, and estrogen is protective to the hearts and the cardiovascular system. You don't have to know why it's protective. I'm not really sure why it's protective, but estrogen is protective somehow. So for women, the risk factor is in total 55. But this is a non-modified risk factor. You can't do anything about this risk factor. As you just grow older, you get an increased risk for heart disease. But by itself, just one risk factor doesn't really matter. Another risk factor is family history, whether anyone in your family has had a heart attack or any cardiovascular problem. But most likely they've had a heart attack. So for men, it's again lower than women. So if anyone in the male's family, usually if their father or brother, this has to be their first relative or the father. So if their father or brother has had a heart attack before 55, that's considered a risk factor. Because if they had a heart attack before age 55, it must have been because of a lifestyle factor. So that can pass down genes, whatnot, and that's a risk factor. But above 55, it's not considered a risk factor anymore because that can be because of age, they may have got it or something. But it's not considered a risk factor. Again, for mother or sister, it's before 65 because, again, estrogen. But those are non-modifiable, so no one really cares about them. They're always going to be there. You can't really do anything about them. And now we'll start the first one. That's modifiable. You can do something about it. It's dyslipidemia. You can affect this on. This is a high LDL, a low HDL. Remember, LDL is bad cholesterol. The more LDL you have, when we get to it, we'll explain it, that more LDL is bad. And then with HDL, the less HDL you have, HDL is good cholesterol, so higher is better, but if you have below a certain level, it's considered a risk factor. Or a total cholesterol, if your total cholesterol is above a certain level, it's considered a risk factor. Now all three of these, LDL, HDL, and cholesterol, are considered all dyslipidemia, so you don't have to satisfy high LDL and low HDL. You can have both, but you don't have to have both. If you just have high LDL, but your HDL say is amazing at 100, but you have very high LDL, you're still considered dyslipidemic. So you just need one, either high LDL, low HDL, or high cholesterol to get this 1 point as a risk factor. Because risk factors are just like one risk factor, two risk factors. So it's in a point system. So you just need either a high LDL, low HDL, or high cholesterol and you're considered at risk. Well, that's considered one risk. And now for the numbers, if your LDL is greater than 130, that's 130 is the cutoff range. If it's less than 130, that's still not great because you want less than 100. But if it's less than 130, then it's not considered a risk factor. But if it's greater than 130, then your risk for heart or coronary artery disease increases substantially. So 130 is considered the cutoff range. And for LDL, since LDL is a good cholesterol, you want a high number, usually above 40. But I don't know if you talked about the negative risk factors. But if your HDL is above 60, it's actually considered a negative risk factor. So you can take off a positive risk factor, and we'll get to that at the very end of this. But if your HDL is less than 40, that's considered risk. Or if your total cholesterol is greater than 200. Now for total cholesterol, you can't just take LDL and add HDL. It just doesn't work that way. Because if you remember, someone asked on the Facebook group about HDL2, HDL3, HDL blah 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 4. LDL also has different subclasses, so you can't just take LDL plus HDL because they mean different subclasses. Hypertension, if you have high blood pressure, and you have to know the cutoff for that, 140 over 90 is considered hypertensive, 140 being systolic, 90 being diastolic. Now you can have either a high systolic, so it can be like 141 over 60. So you have high systolic, but you didn't satisfy the diastolic, but you're still considered hypertensive. So you just need one of them. And that's one positive risk factor. If you're hypertensive, that's one positive risk factor, you're more likely to have heart disease. So, and the next one, smoking. If you smoke, or if you're around, even if you're around smoke, secondhand smoke, that's still considered a risk factor within 6 months. So if you just quit and it's been 5 months, it's still considered a risk factor. But if you just quit and it's been 7 months or 6 months and 1 day, it's not a risk factor. But basically, smoke is a risk factor. That's common sense. Everyone knows that. Sedentary, you have to be active 3 times a day, 3 times a week, 30 minutes a day for 3 months. So just 3, 3, 3. So if you're less active than this, 3 times a day for 30 minutes a day for 3 months, it's considered a risk factor. Just remember 3, 3, 3 for sedentary. Obesity, if your BMI is greater than 30, remember that's the cutoff for obesity, that's a risk factor. And the last one's glucose level. If you're IFG or you're fasting glucose, is between 100 and 125. And what this means is you're fasting, so you haven't eaten in 8 hours, they finger prick you, and then they measure it in a machine, how much glucose you have in your blood, and ideally if you're fasting, and within 8 hours your insulin would already been acted, and the insulin would did its thing and brought the glucose into the cells. But so your glucose level fasting will be lower than 100, hopefully. But if it's between 100 and 125, your insulin's not working for some reason, and you still have a lot of glucose left in your blood even after 8 hours of eating. So if it's between 100 and 125, it's considered, you're still not considered diabetic, but it's considered pre-diabetic. So if you don't do anything to fix it, if you don't control your diet or your blood sugar, you will be diabetic in the future most likely. But if it's above 126, then you're diabetic, and that automatically makes you high risk for coronary heart disease. But he didn't talk about any of the high risk, low risk, medium risk. But when you get to exercise testing, you'll have to be able to classify someone based on all 8 of these risk factors and classify them on low risk, medium risk, or high risk. If you're diabetic, you're automatically considered high risk. On the next one, OGTT, or oral glucose tolerance test of 140 to 199. And why this number is so much greater than your fasting glucose level is because the oral glucose tolerance test means they give you something with a shitload of glucose, really like a very, very sugary drink, or you just drink straight sugar. And then they instantly, or they wait, I think they wait 4 hours or something, and then they measure your glucose level, and if it's between 140 and 199, this is considered, again, a risk factor. So basically there's 8 risk factors. It's like a tally system. If you satisfy these criteria, you have one risk, another risk, another risk. And based on how many risks they have, you can classify them as low risk, medium risk, or for high risk if they actually have a symptom of heart disease. You don't have to go over the symptoms. And the only exception is HDL. If you really have, of course, if HDL is low, it's considered a risk factor if it's below 40, but if your HDL is actually above 60, is pretty high, that's considered a negative risk factor, so you can take that off of one of the risk factors. But I don't know how in detail you went into risk factors and what you would actually ask on the test based on risk factors. When I took it, he didn't ask anything about risk factors. Okay, so 15. How does exercise affect these risk factors? Clearly, exercise is good for the hearts. The more cardio you do, it's called cardio for a reason, it works the cardiovascular system. It's extremely beneficial to the heart because it makes the heart more efficient on pumping, all through the second test that I went over. It makes your heart stronger, somewhat bigger, able to pump better, blah, 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 better in its job. It's a muscle, it responds to exercise, so it gets better. So the majority of risk factors can be fixed with exercise. If you just look at them like dyslipidemia, you can lower your cholesterol with exercise. You can lower your LDL, well, not really LDL, that's controlled with diet, but you can raise your HDL with exercise, like everything. So dyslipidemia can be fixed with exercise. You can't really do anything about smoking, you have to stop that, but you can control your blood pressure with exercise. Exercise will lower your blood pressure, so you can fix that. Exercise will clearly lower your BMI, so you won't be obese if you've been exercising, hopefully. And exercise will affect your glucose levels. It'll make your body more efficient at using insulin, so it can reverse diabetes, and it makes your body more efficient at using insulin. So it increases your insulin sensitivity. And you have to know that word, that exercise increases insulin sensitivity. Don't know if you have to know it for this class, but you'll definitely know it for exercise testing. So exercise is good. Okay, 16. Now, why is cholesterol bad? Why do we care about cholesterol? Why is there so much hype about cholesterol? How does it affect coronary heart disease? How does it lead to it? Now, I don't know if you remember from a tab, but cholesterol has a lot of... don't remember from a tab, but cholesterol has a lot of good things. Cholesterol is essential for the phospholipid bilayer, so it's essential in all the cells to make the phospholipids more fluid, so it's essential for that. Cholesterol is essential in the body. It makes bile, so you need bile to digest fat, so you need cholesterol in order to make bile. Cholesterol makes all the sex hormones, so it makes testosterone, it makes progesterone, it makes estrogen, it makes estradiol, it makes cortisol, it makes vitamin D. All of these hormones and vitamin D is based on the structure of cholesterol, so they all they all arise from cholesterol. So cholesterol makes all of these. So if you didn't have any cholesterol in your body, then you can't make estrogen, testosterone, progesterone. You can still make vitamin D, but not as well. So clearly, you need cholesterol. Cholesterol is good, and your body makes cholesterol in the liver. So if your body makes it, it must be good. But like anything, if you have too much of a good thing, it's bad. So if you have too much cholesterol, it's bad. And the first part of the question explains everything I just said about how cholesterol is good. It makes all those hormones are considered steroid hormones, or sex hormones is considered the same thing. So cholesterol has important parts of the body. Now the reason cholesterol is considered bad, because once cholesterol gets above a certain level, what's called your serum cholesterol, serum being in the blood, so once it gets above a certain level, the level is 200. So once it gets above 200, then it's considered a risk for heart disease. The reason being because the higher it is, the more likely it's to be, your body doesn't need it, just like fat. Like if you have too much, fat's essential. If you have too much fat, it's stored in adipose tissue, your body doesn't need it, so it stores it. Same thing with cholesterol. If your body doesn't need the cholesterol to make hormones or whatnot, it'll store it, but it's the place that stores it is bad because it stores it in the coronary arteries. And again, the coronary arteries supply blood to the heart, so if you store cholesterol in the coronary arteries, you'll occlude the blood flow to the hearts, because you don't need cholesterol in the coronary artery. It's just going to get there and stop the blood flow and occlude it and form a plaque. And now to get into more detail, we'll get into more detail and get to the lipoproteins about how cholesterol gets into the arteries and how it actually causes atherosclerosis or hardening of the plaques and actually makes a plaque. Hardening of the coronary arteries and actually makes a plaque in the coronary arteries. And it does it through a specific mechanism. So the higher your cholesterol is, this mechanism depends on cholesterol, so the higher, or depends on LDL, which LDL arises from cholesterol. So if you have high cholesterol, you have high LDL. That's just how it is. So we'll go over that when we get to that question. So high cholesterol is positively related to coronary heart disease, or CHD. Okay, so now he goes over briefly that running lowers cholesterol somewhat. Cholesterol is mostly, since cholesterol is made in the body, you always have a set amount that's made in the body. And someone usually has high cholesterol not because of the diet, it's because the body makes too much cholesterol or anything. Because the diet, cholesterol is not really found in a lot of foods in your diet, but that's getting into too much detail. But mostly cholesterol is you have high cholesterol levels because something's wrong with your body and it's making too much cholesterol. So you take a drug called a statin. And the physiology of a statin is it stops the production of cholesterol. So it stops the rate-limiting enzyme that makes cholesterol. So if you decrease the activity of this enzyme, you'll make less cholesterol. That's how statins work. But running lowers cholesterol somewhat. So it's beneficial to lower cholesterol, but once you stop running, you immediately go back to the level you were before. So really, you just want to be more active to lower cholesterol. But once you stop exercising, you pretty much lose all the positive effects. And you all know this, once you stop exercising, you have the reversibility thingy, so you'll just lose pretty much all your gains eventually. And again, smoking, so smoking sucks, don't smoke. Okay. 17, what role does smoking have in cardiovascular disease? Why is smoking bad? Smoking's bad because, well, first off, it lowers tobacco or the carbon monoxide, and the tobacco displaces oxygen on the hemoglobin when we talk more about altitude at the very end of it, but it displaces oxygen on hemoglobin. So it has carbon monoxide has a higher affinity for oxygen. So carbon monoxide will rush to the hemoglobin and bind to it, so oxygen can't bind to it. And this is clearly bad because it's going to lower your oxygen consumption on hemoglobin. So the carbon monoxide binds the hemoglobin faster. For numbers about 1,000 times greater than oxygen. So the more you smoke, the more carbon monoxide you have in your system, and the more it's going to bind to hemoglobin. And which is why carbon monoxide is a poison and it kills you. That's one thing of how it displaces oxygen, but that really doesn't relate to atherosclerosis. It just affects your oxygen. And how it relates to atherosclerosis or the hardening of the arteries is because cigarette smoke or the tobacco will actually damage the epithelial of the cell or the lining of the coronary arteries. And then again, the coronary arteries is just like a little tube that carries blood to the heart. And when the walls of the tube or the epithelial get damaged, this will start the cascade when we get to it of atherosclerosis. So once you damage this lining, that's bad. And the things that damage it are oxidized LDL when we get to it, but cigarette smoke is a big thing that damages the artery, so stop smoking. So once you damage everything, you start the cascade, blah, blah, blah. Okay, so now 18. Okay, what are HDL and LDL and how do they affect atherosclerosis? Now we can actually talk about the mechanism of how LDL deposits cholesterol. So LDL is considered bad cholesterol once it gets to a certain level because it goes and deposits the cholesterol, and so it just dumps the cholesterol into the coronary arteries because you have too much cholesterol. HDL is like the cleanup guys, so they come around and pick up the cholesterol from the coronary arteries before it has a chance to occlude it and excretes it in the body or recycles the cholesterol. So more HDL is good. Lipoproteins, I'm sure you remember from metabolism, but lipids are different than all the other macronutrients. They're non-polar, which means they can't travel, and lipids being fat, so they can't travel in the bloodstream, so they need these lipoproteins or these capsules. It's normally LDL. It starts with a VLDL, goes to IDL, and then gets to LDL to travel in the bloodstream to different organs. So lipoproteins are essential. But once you have too much LDL, it's because you have too many cholesterol, because LDL is considered the cholesterol transporter. Because they start as transporting fat, but eventually they start transporting cholesterol, and then once they start transporting cholesterol, that's when we care about them for this class. And then my guy also goes over like lipids first. They travel from the liver, and the liver they're packaged into lipoproteins. They start with VLDL, go to different body tissues. You have the lipids slowly leave the lipoprotein, and the composition of VLDL, the density will get lower, or get a little higher, sorry. So the density will get a little higher, it'll go to IDL, and then it'll go to LDL, and LDL is what we care about. Now when it's LDL, it's transporting mostly cholesterol, because the lipids have left when it was VLDL, so now it's transporting mostly cholesterol. And it's depositing that cholesterol in the arteries, most likely in the coronary arteries. And when you deposit the cholesterol is just going to build up, build up, build up. And HDL again picks it up. So we're going to talk about the cascade. And now for the subfractions. Subfractions, the second part of the question, are like the different, because HDL is considered good lipoprotein, but there's actually different densities of HDL, like HDL2, HDL3, so it's different densities that they don't really talk about. So we all know we want low LDL, low bad cholesterol, and high HDL, or high good cholesterol. And now you have to know the things that affect LDL and the things that affect HDL. LDL is mostly linked to a diet, so no matter how much you exercise or do resistance training, LDL usually isn't lowered or raised based on exercise, how much exercise. It's usually raised based on your diet. And HDL is usually raised based on your physical activity. So foods don't usually, not that I know of, there's no food that you can eat to raise your HDL, or you can't control HDL levels with your diet. You can control with medicine, of course, but it's related to your exercise, how much you exercise. More specifically, how much you do aerobic exercise. Aerobic exercise, cardio makes your heart stronger, and just think HDL is linked to the cardiovascular system to decrease the risk for coronary heart disease. So aerobic exercise affects HDL levels. The more you run, the more you bike, the more you swim, the more positive effect you have on HDL. Now, because of the subfractions, HDL is actually divided into high density HDL and low density HDL. And HDL2 is considered the larger HDL, so that's considered more beneficial. But I don't know how much in detail you went to that. Okay, so remember, more LDL, the more cholesterol you'll deposit into your coronary artery. The more cholesterol gets deposited, the more you'll form occlusion, or you'll block blood flow because you form a plaque. And you occlude blood flow. When you occlude blood flow completely to the heart's going to die. Again, 19 is pretty much talking about what I already explained about how the risk factors affect each other, how they interact, where if you have one risk factor, most likely you have another risk factor. Unless they're non-modifiable risk factors, if you're just like above 45, more than likely you don't have any other risk factors. But if you have one risk factor, like if you're obese, you usually have many more risk factors. So thus, it's a multifactorial disease. They always refer to it as a multifactorial disease. All the factors influence one another, etc. Blah blah blah. If you're diabetic, or if you have high glucose, most likely you have high blood pressure, most likely you're obese, everything. Okay, 20. What is the significance of understanding the relationship between high cholesterol, total cholesterol, HDL, and LDL? Again, this is pretty much just asking the same thing why we care about it. Where HDL is good cholesterol, you want high HDL, you want low LDL or bad cholesterol, and you got to know the ranges probably. You want below 130 LDL, you want above 40 HDL, but above 60 is even better. You just want high HDL. Total cholesterol, you want below 200. So the way he's going to ask it, he's going to use the word inversely and aversely related. So HDL is inversely related to coronary heart disease, or it's inverse. So the more HDL you have, the less risk you have. Whereas LDL is positively related or adversely related. More high LDL, higher risk. And the other numbers he gave from my class are the ratios of total cholesterol to HDL, with the idea that if it's not HDL, it's an LDL, so you want the ratio. So you want a low ratio of like 5:1 versus 20:1. If you understand these numbers, what this means, 5:1, the number on the left being 5 being how much your total cholesterol. So you take 5 molecules of, you take 5 lipoproteins or 5 whatever, and within those 5, one of them is an HDL. So and then you take 20:1, you take 20 cholesterol or lipoproteins, and you take 1, and then out of those 20, you have 1 HDL. Clearly, the 5:1 is better than the 20:1 because you want less, you want more HDL than not. So lower ratio is better, total cholesterol versus HDL. And things that affect these lipoproteins: physical activity, I already went over this. Cardio, aerobic activity raises your HDL. Kind of briefly, if you can draw conclusions, premenopausal women, estrogen. Estrogen is protective against coronary heart disease because it raises HDL. Don't know how HDL is related to estrogen, but the more estrogen you have for women, the more HDL you have because they're just related. Alcohol, it's considered bad, so it lowers, and the reason is because it raises LDL. And of course, steroids are bad. Because the reason they're bad, they do many things, but they lower HDL. So we don't want to take steroids because it can raise your risk for heart disease because it can lower HDL. So those are things that can affect HDL. Exercise, good, or cardio exercise, aerobic exercise, good because it raises HDL. Estrogen raises HDL, so for mostly premenopausal women. Alcohol raises LDL. You can just think that easy because it's common sense. The more alcohol you drink, obviously, not the more protective against heart disease, so alcohol can't raise HDL. And steroids, everyone knows, are bad for you, so most likely they're going to lower HDL, so they lower HDL. 21 talks more about estrogen, but I didn't really, I just said we don't know why. Kind of going over again, why women have lower risk for heart disease than men because of estrogen. You have to know that because of estrogen, and the most good best estrogen, it affects HDL. Now 22. 22 is talking specifically about what the lipoproteins do, what does LDL do, and what does HDL do. Kind of went over already, but lipoproteins transfer lipids in the bloodstream. That's the purpose. Since lipids are nonpolar, they can't travel in the bloodstream, so you need these lipoproteins to transfer them in the bloodstream. So you consume lipids it's asking about all the lipoproteins. So first you consume lipids, and you have to get the lipid from your small intestine to your actual liver. So in order to get to the small intestine to the liver, first it goes into the first lipoprotein called a chylomicron, which a chylomicron transports exogenous lipids. And you know metabolism, you know exogenous, but it just transports the lipids you're eating. So chylomicron just brings it to the liver. And then once it gets to the liver, the chylomicron's done, and now it gets packaged. It has to go to the tissues. So now the lipid gets packaged into a VLDL, and the VLDL brings it to the tissues. And now to get the lipids out of the VLDL, it's cleaved out, and eventually when you lose lipids, you keep constantly losing lipids, the composition is going to change, so now it's mostly, the lipoprotein is mostly transporting cholesterol. Because lipoprotein is made out of cholesterol triglycerides, and proteins in different compositions. And chylomicron having mostly triglycerides because it's bringing it to the liver, and then VLDL having, again, mostly triglycerides because it's bringing it to different tissues, or it's transporting the triglycerides. But LDL has mostly cholesterol because now you cleave out all the triglycerides from the VLDL and the composition changed. So now the LDL has mostly cholesterol. So what's the LDL going to do with that cholesterol? The LDL has no place to put it, so it's going to deposit the cholesterol to the coronary arteries. So it's just going to dump the cholesterol into the coronary arteries. And then HDL is going to come around. It's a separate lipoprotein made in the liver. It's going to come around and pick up that cholesterol that the LDL is just deposited. And it's going to recycle the cholesterol, bring it to bile, or excrete the cholesterol. So LDL is the good dude, LDL is bad. Well, HDL is the good guy, LDL is bad. Okay, so that's everything about the chylomicrons. So I guess you don't have to know the mechanism behind atherosclerosis of how it starts. Just know once cholesterol gets deposited into the blood or onto the walls of the coronary artery, bad things can happen. More cholesterol usually means bad because first, just go over it briefly in case he does ask it. When you deposit cholesterol, when LDL gets oxidized, and different things will increase the chance of it getting oxidized, like more cholesterol, smoking. But once LDL gets oxidized, like your body has a protective mechanism with macrophages and all that stuff, and monocytes and neutrophils, and all that stuff will rush to the oxidized LDL, where the cholesterol is inside the coronary artery, because your it's an injury site. So all the monocytes and everything rush to that damaged area to try to fix it. So, but all these good cells, these monocytes and macrophages and neutrophils, will actually they're useless kind of, so they just clump together they just clump together and form a big mass, a mass of shit. So they just clump together. But eventually this mass of shit is going to explode, and when it explodes, it's going to release all of its contents onto the wall of the artery, and that's how you form plaque. And cholesterol starts all this. Cholesterol and oxidized LDL. And that's just the mechanism behind atherosclerosis. Now 23, so exercise and environmental stress. 23 is know the 4 factors to contribute heat gain and heat loss. And now these 4 factors are kind of like a review in chemistry. Now, when I took this class, he didn't talk about this section at all, so I just took these questions, well, 23 and 24, I took those and copied and pasted them from another guide I wrote based on heat loss from the anatomy guide, my anatomy guide. So these might not be too close to what he talked about in class, but first, the things that make heat in your body, your basal metabolic rate. Every time you have a metabolic reaction, you create heat. Heat is a byproduct of everything in your body, of every reaction, and heat is useless in your body. Your body can't use heat for energy, so it's just a useless byproduct. So you create heat every time you move, every time you cleave ATP to contract a muscle, every time you do all these things, you create heat. And now the 3 things that contribute to heat gain and heat loss are evaporation. Evaporation being when you sweat. So you sweat, you don't lose your body doesn't cool until the sweat evaporates into the air. When it evaporates, you lose heat. Another one is radiation. And radiation is just a transfer of electromagnetic rays that's mostly for heat loss, whatever. Convection, which is again air moving, and the easiest one, conduction, is a transfer of heat from a hot object to a cold object, or from hot to cold. Okay, so now I don't know how in detail you went again, but I just went over see what happens when you're hot, what happens when you're cold, how's your body fix that. When you're hot, the way it works is your hypothalamus controls the body temperature, so your hypothalamus sets a body temperature set point. And this set point is 98.6, it's the normal body temperature, and that's the set point. And when your body temperature raises above 98.6, your hypothalamus recognizes this and it recognizes the increased body temperature, so it wants to lower this increased body temperature because if the body temperature increases too much, that's bad. It'll start denaturing proteins and everything. So the hypothalamus senses this, and it's called the hypothalamus heat loss center because you want to lose heat if it gets above 98.6. So the hypothalamus senses this, and it's going to do a few things. It'll activate your sweat glands and all your muscles, so you're more likely to sweat. And then you sweat, and the sweat evaporates, and you lose heat, and then you fix the problem. And it'll also vasodilate the vessels going to the surface of your body, Because when you vasodilate a vessel, it opens the vessel, and when you open the vessel and make it wider, more blood can flow to the surface of your body. When more blood flows to the surface of your body, blood brings heat. Heat travels in the bloodstream, so more blood that flows to the surface of your body means more heat is going to the surface of your body. And if heat is closer to the surface of your body through radiation, the heat is just going to radiate off your skin pretty much. Heat's going to leave your body this way. So vasodilation will increase heat loss in the body. And through vasodilation and through sweating, you lower your body temperature, or you control your body temperature in that very narrow range of your hypothalamus that's considered homeostasis. So this is all to restore homeostasis. So if you're too hot, you want to restore homeostasis, so you sweat or you vasodilate. This is done by the hypothalamus. Now if you're too cold, you want to again restore the homeostasis, so you want to warm up your muscles. So the same thing happens if you're too cold. You have baroreceptors, chemoreceptors. You just have these different receptors that will alert your hypothalamus. But instead of activating your heat loss center, you want to activate your heat gain center. You want to gain heat. So you want to do anything that can gain heat to your body instead of activating your hypothalamus, instead of activating the sweat glands, because you don't want to sweat when you're cold. You want to, it activates your muscle, it causes them to shiver and contract very forcibly, very fast. And this will cause your muscles to create heat, because if you remember, every time you contract your muscles, you create heat. And it will also, instead of causing your skin to your vessels to vasodilate, or cause your vessels to vasoconstrict. And if you vasoconstrict your vessels, less blood flow is going to the surface of your skin, so you're going to lose less heat through radiation. But also more, if you vasoconstrict your vessels going to your skin, like the cardiovascular system, like if you vasoconstrict somewhere, you vasodilate somewhere. It always controls blood pressure. So if you vasoconstrict going to your skin, you vasodilate going to the essential organs. So it vasodilates the vessels going to your liver, to your kidneys, to your heart. So, and the vital organs. And this is going to shunt the blood to those organs in order to cool up your body. And then when you, or to warm your blood. And when this happens, it raises the blood to the set point, and that's good. So the hypothalamus keeps your body in that homeostasis. And then I don't know if you talked about hypothermia and everything, but if your body gets too hot, if this heat loss center is not working and your body, first you get above 98.6, that set point, but your hypothalamus isn't losing heat fast enough through sweating and vasodilation, not losing heat fast enough. Once your body temperature gets above a certain level, I have above 1.105. Once it gets above that, then that's bad, because your body is so hot, protein starts to denature, the body starts destroying itself pretty much. And that's just hypothermia. Now it's considered heat stroke. When it's considered heat stroke, that's when your organs have started to damage themselves, your proteins have started to denature. That's bad. Hypothermia can be reversed. It's heading to to heat stroke. It could be reversed. Nothing has damaged itself yet, but it's bad. It's like a warning zone. But once you get to heat stroke, then you've already damaged muscles, you damaged organs, you damaged brain cells probably. Now hypothermia is just the opposite, you're too cold. Okay, the other two questions I said I couldn't answer, but I ended up answering them on 28, so we'll just skip the 28. 28 is, what is the consequence of dehydration on your performance and your physiology, and why is dehydration bad? Why do you want to control the fluid level in your body? Now the reason being because when you're dehydrated, it leads to a whole cascade that at the very end will decrease performance and cause health problems. And I don't know if you have to know, when you get dehydrated, you mostly lose water inside your cells, so the intracellular compartments. Now the cascade is, okay, so blood pressure is just the pressure of blood on the walls of the arteries, and blood is a fluid. So that follows that the more fluid you drink and the more liquid you have in your body, the more your blood pressure is, and that's what controls your blood pressure or fluid. So when you get dehydrated, your blood volume is decreasing and you're lowering your blood pressure. So first you say you're dehydrated. This will decrease your blood volume, because blood volume is a fluid. So you're getting dehydrated to a certain extent and you're decreasing your blood volume. And if you measure someone, they have a low blood pressure when they're dehydrated. So you're decreasing your blood volume. Now when you decrease your blood volume, if you remember from the second test about the cardiovascular system, how it works, it's a closed loop. So when you decrease your blood volume going from out your aorta to your arteries, you would decrease your venous return and you have less blood going back to your heart. Since it's closed loop, you're losing blood volume, so you're just going to have less go back to your heart. If you have less blood going back to your heart or decreased venous return, you have less blood to pump out since it's a closed loop, so it'll decrease your stroke volume, with your stroke volume being how much blood you pump out with each beat, so you have less stroke volume. So dehydration is going to lead to less stroke volume. And now what's going to happen if you have less stroke volume, if you remember from the formula for cardiac output is equal to heart rate times stroke volume. So your body wants to maintain cardiac output when you're exercising because cardiac output is supplying the blood to your muscles. So you want to maintain this output when you're exercising. So if you decrease stroke volume because of this formula, heart rate will increase to try to maintain that cardiac output. And when heart rate increases because of a lowering stroke volume or a lowering blood volume, that's called cardiovascular drift. So your heart is slowly drifting to a higher heart rate because of the lower dehydration, lower blood volume, and thus a lower stroke volume. So your heart rate will increase to maintain the cardiac output. But your heart rate can only increase so much, and eventually it won't be able to keep up with the lowering stroke volumes because your stroke volume is still going to be decreasing at the same rate that you're being dehydrated. So the more you're sweating, the more your blood volume is decreasing, the more your stroke volume is decreasing, the more your heart rate is increasing. So that is actually why once you reach a steady state during exercise, once your heart rate is done increasing to a certain level, and then say you've been exercising for 30 minutes at a certain heart rate, and your heart rate slowly starts increasing. And this is why your heart rate starts increasing, because you're sweating when you're working out, and when you're sweating, you're actually losing blood volume, so your heart rate will increase to maintain that decrease in stroke volume, to maintain that cardiac output. So everyone does cardiovascular drift usually when they go for, like when they're running for 30 minutes or an hour or something, or exercising for an extended period of time. But eventually the heart rate can increase so much because they have a max heart rate. So this will lead to the heart will back off. It'll be like, I don't want to increase too much, so it'll back off. And when you start decreasing your heart rate, you start decreasing your cardiac output, and when you start decreasing your cardiac output, your muscles start getting less blood, and when they get less blood, they can't exercise. So thus you will cease exercise. So let's see, I'm good, I covered it. So first, you decrease blood volume because you're dehydrated. If you increase blood volume, it would decrease venous return, then you decrease stroke volume. If you decrease stroke volume, your heart wants to maintain that cardiac output, so you will increase your heart rate in return in response, and that's called cardiovascular drift. But eventually you can't keep increasing your heart rate. Your heart will realize this and you'll stop increasing your heart rate, and thus you'll decrease your cardiac output and you'll cease exercise. And that's what happens when you're dehydrated. And I explain more about what cardiovascular drift is. It's when heart rate increases with sustained exercise because you sweat and your blood volume decreases and your stroke volume decreases. Okay, then I don't know if you need no numbers, but for dehydration, you obviously want to avoid dehydration when you're exercising because of this reason. If you drink water when you're exercising for a long time, you can actually prevent cardiovascular drift by increasing your blood volume, because as you lose fluids through sweat, if you intake fluids, you increase your blood volume. And I had numbers here, 1 pint for every pound lost. That's like a universal number usually. And the universal number for how much body weight you want to avoid losing, because once you lose body weight past this, they always measure how much body weight you lost compared to how much you weigh before exercise and how much you weigh after exercise. And you want to avoid a 2% loss in body weight, because once it gets over 2%, then you start negatively affecting performance. And that's for like running and whatnot. Now, if you're weight training, if you're like strength training, resistance, and you're in the gym, you don't start affecting your performance until 3 to 5% loss. But I don't know if he gave numbers, and you have to know the numbers. But 2% is considered the universal cutoff for endurance training, and 3.5% is considered the cutoff for resistance training. You don't want to lose more than this body weight. Okay, 29. What happens when you get used to exercising in the heat? When you first introduce in heat, the whole thing about the previous question, it's you will lose blood volume and blah blah blah, cardiovascular drift, cease exercise. So when you first go in heat, that's what happens. Now, if you keep exercising in heat, eventually your body adapts. The body is very versatile, so it'll adapt to any stress. So if you keep exercising the heat, it will suck in first, but your body will adapt to it, and it usually takes 10 to 14 days to adapt to it. And what happens and how the body adapts, you will sweat more, obviously, because you want it. And you will sweat more. That's one way your body will adapt, and you will also conserve electrolytes. But I don't know if he talked about that, of how what your body actually does. But you sweat more and sooner. So pretty much, the sooner you start exercising and then you acclimatize the heat, you will sweat sooner during exercise. Okay, at first that didn't make sense. I'm like, what? The reason being because if you sweat more, like say you just reach high altitude, you don't start sweating until 10 minutes into exercise. So during those 10 minutes, your body temperature was increasing drastically during those 10 minutes because you're not losing body temperature or body heat, because you lose heat through evaporation of the sweat. But now say you acclimate, you've been in the heat for 10 to 14 days, so your body's adapted to exercising the heat. So now you start sweating within 2 minutes of exercise. And the reason why this is considered beneficial to the body, because again, evaporation, the sooner you sweat, the more you release heat. So if you sweat within 2 minutes, you start losing heat within 2 minutes. So it cools your body. So sweat cools your body, obviously. So the faster you sweat and the sooner you sweat during exercise, the sooner you cool your body, the more beneficial you are to preventing dehydration and lowering blood volume and cardiovascular drift. Now 30 is the next question, which I think is the most important question that he loves asking questions on: how exercise affects altitude, how altitude affects breathing, hemoglobin, saturation, and the Bohr effect isn't really altitude. We don't want to talk about that. But it's how altitude affects breathing and why it's so hard to breathe in a high altitude. So identify and discuss the effects of increasingly high altitudes on ambient partial pressure of oxygen saturation, and of hemoglobin, and oxygen in the pulmonary capillary, and VO2 max. Okay, so first we'll go over the basics of how oxygen is transported in the air, how our body gets oxygen, and how it enters the arterial bloodstream to go to the tissues and everything. So first, we have, say we're at sea level right now, so we are in sea level, but oxygen in the air is measured in partial pressure. Partial pressure being the pressure that all the oxygen in the air is giving off. And this pressure is 160 milligrams of mercury. So anywhere in sea level, this pressure will always be 160 milligrams of mercury. And this number, the partial pressure in the atmosphere, so I just call it atmospheric partial pressure, there's a formula for it. It's the percentage of oxygen in the air, which is always 21% no matter where you are on the earth, whether you're on sea level or you're 10,000 feet in the air. It's always going to be 21% or 0.21 times 21% or 0.21 times the barometric pressure. And the barometric pressure changes or gets lower with altitude. So at sea level, the barometric pressure is 760. That might be the only number you have to memorize, 760. And it decreases higher you get. So you get to 5,000 feet elevation. It decreases, say, to 400. You get to Mount Everest, so it'll decrease to 200. It'll just keep decreasing. And because of this formula, since barometric pressure is decreasing with altitude, and the pressure of the oxygen percent in the air is always constant at 21%. At sea level, you have 0.21 times 760. If you do the math, that's 160 milligrams of mercury. So the atmospheric pressure is 160 anywhere on sea level. But if you go to, say, Mount Everest, where the barometric pressure is 200, or somewhat. So you take 200 times 0.21%, because it's still 0.21%, and that's a very low partial pressure. It's like 70 or something like that. I'm not sure. It's a very low partial pressure. Actually, that's 40. So it's a very low partial pressure. And so the higher altitude you get, the lower the atmospheric pressure is going to get. And why this is bad and how this affects everything will be explained next. So you have your atmospheric pressure of 160 milligrams of mercury, but that's in the atmosphere. What happens when you actually inhale it and everything? What happens to the pressure? Decrease. So now you inhale it, it goes into your alveoli or the sacs in your lungs, and when you inhale it, the partial pressure decreases. And you don't have to know why it decreases because it doesn't ask it, but it decreases to around 104. So it'll go from 160, you inhale it, it gets inside to your lungs, and it decreases to 104. So it just decreases. Now, since this is called P big AO2, how you can refer to that, or an easy way to remember is big A stands for alveoli. So it's the partial pressure in the alveoli of the lung. Whereas little AO2, when we get to it, is arterial, or the partial pressure in the arteries. And the arteries are different than the alveoli, where the alveoli is in your lungs, the little sacs, and the arteries are actually the blood and the vessels going to different tissues. So you start at 160 in the air, you inhale it, it decreases to 104. So now it's always going to decrease. So because of this, in sea level it starts at 160, it decreases to 104. So I don't know other numbers for, but say Mount Everest, it's too high. And somewhere else where it's not as high as Mount Everest, say the partial pressure is 90. So it's starting at 90 instead of 160. It's still going to decrease when it goes into the body, so now it decreases to, because it decreases from 160 to 104, so that's a decrease of 60 milligrams of mercury, so it's going to decrease from 90 to 30, say. Or it probably won't decrease as much, but it will still decrease when it goes into the blood, the alveoli. So at the end story, it decreases. So the higher altitude you get, the lower your atmospheric pressure is, the lower your alveoli pressure is, or the P big AO2. And now, once it's in the alveoli, it has to diffuse into the bloodstream or into the arterial blood, so it'll diffuse into the arterial blood. And now when it enters the bloodstream, again, the pressure will drop to 100. So it goes from the alveoli at 104 pressure to the actual bloodstream and the arteries to 100, so it drops. So it's always dropping as it moves through the body. So it goes from 160, 104 to 100. Now since it always drops, what happens, the higher altitude, you have a low atmospheric pressure of say 90, it'll still drop when it goes to the alveoli, like 60, it'll still drop when it goes into the arterial blood, say 56. So it drops, 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 drops. Now the reason why I'm explaining all these dropping will now make sense finally. So now when it gets into the bloodstream, the oxygen has to travel on hemoglobin, or the transporter, to get to the organs. Now hemoglobin can hold 4 oxygen molecules, and depending on its percentage of how saturated it is, or how full of oxygen it is, that's considered hemoglobin saturation. You want high saturation, obviously. The more saturated it is, the more oxygen it's carrying, the more oxygen it can bring to the tissues. So you want it more saturated. And the saturation depends on this arterial partial pressure, or the P little AO2. So in sea level instance, we started at 160, went to 104, went to 100. And 100, based on the little graph, the graph shows like how saturated it is at a certain partial pressure, and then it goes down. So it's a sigmoidal curve. It's pretty around 95% saturated until it gets to a certain partial pressure, and then it drops substantially. And this is kind of good. So this little curve it starts at 100 milligrams of mercury, where it's 95% saturated. That's so sea level. And the higher and higher you get, the more and more and more this partial pressure will drop. But because this sigmoidal curve, we have that flat portion of the line, the oxygen saturation isn't really going to be affected until it reaches a very low partial pressure or a very high altitude. So that's why at sea level you can pretty much breathe the same as you can at 2,000 feet, because that doesn't really affect the partial pressure as much as, say, sea level to 5,000 elevation. But once it gets to 5,000 elevation, it affects the partial pressure greatly, and then it reaches that steep curve. You have to look at the graph to understand that. So the pressure drops once it enters the blood. Okay, so once it's traveling in the bloodstream and reaches the capillaries, it diffuses off out of, I don't think you need to know that once it enters the capillaries, but it diffuses off out of hemoglobin because of another concentration gradient. And then in the veins, now in the venal blood, the partial pressure is 40 milligrams of mercury. And then it goes back to the lungs and it repeats the process. So it starts at 160, goes to 104 in the alveoli, or the P big AO2, goes to 100 in the arterial blood, or the P little AO2, binds the hemoglobin based on that little dissociation curve of 95% saturation, because of hemoglobin saturation depends on the arterial partial pressure of oxygen. So in the arterial partial pressure is affected by altitude. So the higher altitude the higher you are in sea level, the lower the partial pressure is in the alveoli, and thus the arterial blood, and the lower the partial pressure is, the less saturated hemoglobin will be. And if hemoglobin is less saturated, it gets less oxygen to the tissues, and thus that's bad. Can't breathe. So why it's hard to breathe at a very high altitude, because you have less oxygen in the air, or you have less partial pressure of oxygen. So the pressure is lower, thus it's going to bind to hemoglobin less. So that's physiologically what's happening with high altitude. It can't bind to the hemoglobin because of the partial pressure, because of the barometric pressure, which is decreasing it. So just to review, blah blah blah, barometric pressure decreases, the atmospheric partial pressure will decrease, lower PaO2 hemoglobin will not be as saturated as much, you decrease hemoglobin saturation, that's why it's so hard to breathe at altitude. Now VO2 max will also decrease with altitude. If you can't breathe, as VO2 max is how much oxygen gets to your tissues. So common sense, if you can't get oxygen to your tissues, if you can't saturate the hemoglobin, clearly you're going to have a lower VO2. So VO2 is going to be lower at altitude because you can't get enough oxygen to your tissues. Okay, 31. Discuss oxygen transport at sea level compared to 16,000 feet. Now, if you understand the concepts from the previous question, this is just taking a comparison at sea level compared to 6,000 feet. Now, at sea level, the barometric pressure is 760 milligrams of mercury times that how much percent oxygen is in the air times 0.21. That gives a partial pressure of 160 milligrams of mercury, atmospheric pressure of oxygen at sea level. So because it's 160 milligrams of mercury in the atmospheric pressure, you breathe it in the alveoli, it's going to decrease to 104, and then it goes to the arterial blood and decreases again to 100. Now, because of that, now at 100 milligrams of mercury, oxygen saturates hemoglobin around 95%. So hemoglobin saturation is around 95% at 100 milligrams of mercury. So that's good. Oxygen saturates the hemoglobin. Hemoglobin moves oxygen to the tissues. Blah blah blah. Good for you. You gain oxygen. Now at 16,000 feet of altitude, that's very high up. At this point, the barometric pressure is very low. So because the barometric pressure is very low, the atmospheric pressure is going to be low because it's still 21% oxygen. So the atmospheric pressure now, instead of being 160 milligrams of mercury, is 90 milligrams of mercury. It's a good number, so it's very low. Now, because it started very low, it's going to decrease even lower when it gets into the alveoli and it gets into the arterial blood. So now, say in the arterial blood, it's around 60 milligrams of mercury, very low. Now, if you look at the curve, just go from 60 milligrams of mercury, see how saturated hemoglobin is. At 60 milligrams of mercury, hemoglobin is only going to be like 40% saturated. And this is not good, so you're only getting 40% of the oxygen you're breathing into your tissues. Whereas at sea level, you're getting 95% of the oxygen you're breathing. So this is why it's so hard to breathe at altitude. Okay, so now what are the intermediate and longer term adjustments to altitude exposure? Now this question, I don't really know, because he didn't go over it at all, and I didn't really want to look in the, I didn't really feel like looking in the book for it. But the simplest effect is your body adapts to it. So if your oxygen saturation is low at altitude, you can't get enough blood oxygen to your tissues, you're going to want to fix this by making more red blood cells. If your body has more red blood cells, it has more hemoglobin to make up for the fact that it can't bind as well as it can at sea level. So more hemoglobin will increase, well, it won't increase the hemoglobin saturation, but more hemoglobin means you get more oxygen. So it's trying to make up for the fact that you can't really bind based on the number. So the body's trying to do quantity over quality of the binding, so it increases the red blood cells. And this is why people train at altitude to get benefits. They go back to sea level to race, endurance events, and increases the blood volume because in altitude your body adapts to it by making more red blood cells. So when you get to the low altitude, like, your body's not just going to kill those red blood cells and adapt to the low altitude right away. So your body's going to keep the red blood cells, and thus when you're exercising at low altitude, your body's more adapted and it's exercising. Now, the very last question about the Facebook thing, about how altitude affects blood pressure. And when you first climb up to a higher altitude, your body will increase in blood pressure immediately. The reason your blood pressure increases when you go to a higher altitude is because, if you think about it, blood pressure is just the force of blood that's against the artery walls. So it's kind of how hard your heart is beating, how much blood you have in your system. So if we already know that altitude, the higher you go in altitude, the harder it is to breathe. And so you have your hemoglobin's not as effective, it's hard to breathe. So your body is going to respond to this by increasing your heart rate. Your heart's going to pump faster and push more blood through your arteries in the hope that more blood will increase your chances of breathing better, because more blood equals more red blood cells. So your heart is going to work harder and pump more blood through its system. So if your heart pumps more blood is going to increase your blood pressure, and this will increase your blood pressure. Now, in the long term, your body adapts to it, like we just said. When your body adapts, it's going to adapt, so it's going to decrease. You're going to decrease your blood pressure. Okay, well, that is everything. Yep. So good luck on this test. I have no idea what the final is going to be, or I'm assuming the final is cumulative, but you have after this test you have a week before final, so all next week is just going to be review. Because in my class he never went over any more material, so I'm guessing that you just have a week of review of just Eddie giving review after review after review. That'll be good. Okay, well, if you have any questions, just ask on Facebook, whatever, I'll just answer it right away.